about how to use polar coordinates to describe the location of a point. One way to describe the location of a point is to use the Cartesian plane. The location of a point on the Cartesian plane is referred to using a coordinate point x comma y, where x is the horizontal distance from the origin and y is the vertical distance from the origin. Another way to describe the location of this point would be to use the polar coordinate system. The location of a polar coordinate system is in with reference to r, which is the radius of a point from the origin, and theta, which is the angle between the x-axis and the radius. For a polar coordinate, each point is determined by a distance and an angle. A polar coordinate pair, r comma theta, determines the location of the point. Again, r is the distance from the origin to the point, and theta is the angle between the x-axis and the radius. If we wanted to graph the polar coordinate 2 comma pi over 4, 2 is the radius, pi over 4 is the angle in between the x-axis and the radius. Some curves are easier to describe with polar coordinates. R equals f of theta is the polar function in which the length r is a function of the angle. If we wanted to plot the function r equals sine theta, we would plug in the values of theta into the function. So for example, pi over 6, plug that into sine theta, we would get a radius of 1/2. So to plot that point, we go up an angle of pi over 6, so that's 30 degrees, and a distance of 1/2 away from the origin. We do this again with pi over 4, pi over 3, pi over 1/2, all the way through pi. The shape of this graph is a circle. Typically, we would need the angles between 0 to 2 pi to complete a circle, but our circle was completed from 0 to pi. Why does this happen? So if we had the polar coordinate 2 comma 5 over 4, the distance from the radius would be 2, the angle would be 5 pi over 4. But what about this coordinate pair? What happens when we have a negative radius? So the first thing you do is you still go out 5 pi over 4, and then to make a radius negative, you reflect it over the origin. So the location of this point, negative 2, 5 pi over 4, will be over here. So when we fill out all of the radius values for theta when it's above pi, we would end up with all of the points repeating. Some curves are easier to describe with polar coordinates. So if we had a function r equals a, that would be a circle with the center at the origin. And to graph this onto in your calculator, you need to switch to the mode into polar and make sure that you're still in radians. If we had the graph theta equals theta, this would be a line through the origin with the slope is tangent theta. Here would be the graph that represents the polar functions. 1 is less than r, which is less than 2, from the angle between 0 and pi over 2. So that would look like two circles with the center at the origin. The first one has a radius of 1, the second has a radius of 2, and if we wanted only between 0 and pi over 2, we would just be talking about the first quadrant. We can use different coordinate points to describe the same location. For example, this would be 2, 30 degrees. We could also use -2, 210 degrees. If you went out 210 degrees, you would be in the third quadrant, and then to get back to the first quadrant, you would have a negative radius that would reflect over the origin. We could also use -2, -150. If you ever have negative angles, instead of going counterclockwise from the x-axis, you would go clockwise from the x-axis. There are several different ways to describe the location of this point, and you can see that below. 2, 30 plus 360 degrees, or -2, -150 plus n times 360 degrees. In order to test for symmetry on the x-axis, for example, for r2 cosine theta, if we had symmetry over the x-axis, the point r negative theta would also be on the graph. Testing for symmetry on the y-axis, if r theta is on the graph, then r pi minus theta would also be on the graph. Or -r, negative theta would also be on the graph. And if we had symmetry over the origin, if r, theta is on the graph, then -r, theta, or r, theta plus pi is also on the graph. How to convert to Cartesian coordinates. Remember the unit circle? The radius at any given point is x squared plus y squared. That's the distance formula. The x-coordinate for the unit circle is r cosine theta, and the y-coordinate of the unit circle is r sine theta. These three equations can be used to convert Cartesian to polar or polar to Cartesian. So if we had y equals x plus 2 and we wanted to convert that to polar coordinates, y equals r sine theta, x equals r cosine theta. Get all your r's on one side, factor out an r. The line y equals x over 2 can be represented on the polar coordinate system with the function, with the relationship r equals 2 over sine theta minus cosine theta. You can check that by graphing it on your calculator. If we had the polar r squared equals 4r cosine theta, we can use our three relationships, plug in r squared with x squared plus y squared. R cosine theta is equal to x, and the 4 will stay. And if you subtract the 4x from both sides and complete the square we will end up with a circle centered at 2, 0 with a radius of 2.